So our first example is working with polynomials. Now polynomials basically are whole number exponents, 3x the first minus 2, 2x cubed, maybe an x squared term, something like that. And whole number exponents, no negatives, no fractional exponents. But these are basically the functions that you're used to working with quite a bit from Algebra 2. So the question really is, is there anything we can't fill in for x and get a corresponding y? And with a polynomial, there are absolutely no limits. You can fill in a million, a fraction, a decimal, -1,000,000, anything you want, and you'll get a y back out. So therefore, the limitation is there are no limitations. The domain of all polynomial functions will be all real numbers. So in other words, -infinity to infinity. Our second type of domain algebraically is the simplest of rational functions, and we're only going to be talking about polynomials divided by polynomials. Now, we know a polynomial by itself has an unlimited domain, so all real numbers, we can fill in anything into a polynomial. But a fraction, different story. If we have a variable in the denominator, then we have to look at where the denominator is 0 because that would be undefined. That's going to present in the graph either asymptotes or holes. Asymptotes are relatively easy to see. Holes are virtually impossible to see unless you know they're there. So that's where your algebraic domain comes in and is very important. So in our first example, f of x, basically we find out where 3x minus 2 is 0. So I'm going to say, well, it can't be 0. So if I solve, I'll get x can't be 2/3. Now, if I factored the numerator and found a common factor, then that'd be a whole. In this case, we don't have a common factor in the numerator. So I can tell you graphically there's going to be a vertical asymptote at x equal 2/3. Now, I'm going to go ahead and put this in interval notation. Technically, this is your domain. Okay, but all real numbers except 2/3. But I'm going to go ahead and take it a step further, and I'm going to say if we looked at all the x values on the number line, at 2/3, we're going to have this void. So if I wanted to actually look at this from interval notation, we'd be talking about from here to here, and then from here on, like so. Sorry. So with that in mind, I can say the domain is from -infinity to 2/3. I'm going to skip 2/3, and then I'm going to go from 2/3 to positive infinity. So I have two different intervals in order to skip that 2/3, and then I'm going to put a union in between, and that is my domain in interval notation. My second example, very simply, is x minus 2 can't be 0. So therefore, x can't be 2. You'll find if you filled in 2 in the numerator, you'd get 0 in the top also, which lets me know if I'd factored that numerator, I'd have a common factor. So graphically, this is actually going to have a hole at 2. It's not going to be a curve. It's going to actually be a line, x plus 2 with a hole. Okay, not worried about that so much right now, but basically that's my domain in its simplest form. Once again, if I put that on the number line, it looks similar to above. So my domain is going to be from -infinity to 2. I'm going to skip the 2, and I'm going to go from 2 to infinity. So all real numbers except 2. What's different about our third one is that I have two separate denominators. So I know that the 3x are two separate factors in the denominator. So I know that the 3x plus 1 can't be 0, so x can't be -1/3. And I know that 5x minus 4 can't be 0, so x can't be a positive 4/5. So that is my domain in simplest form, all real numbers except -1/3 and 4/5. If I put those on a number line, So on the number line, I'd put my negative 1/3. I'd put my 4/5, something like that. So this one's going to be a little different, and then I have this section over here. I skip over that one, and then that section there. So I actually have 3 separate intervals. So my domain in blue would be 3 sections from negative infinity to negative 1/3, union negative 1/3 to 4/5, union 4/5 to infinity. And I'm running out of space there, but you get the idea. And that is domain of the simplest rational functions when it's a polynomial over polynomial. Third type of domain algebraically we're going to be talking about are working with radical functions, specifically square roots, cube roots, fourth roots, fifth roots of some polynomial. So I'm going to kind of classify these in 2 categories. We have square root, since square is to the 2nd power. Square root would basically be like a 1/2 power kind of thing. We're dealing with even roots, so square root, fourth root, or I'm going to classify as even roots, and then odd roots are going to fall into its own separate category. Cube root, fifth root, seventh root, those are all going to be the same results. When it comes to radicals, square roots, and fourth roots, we cannot take a number times itself twice, 2 factors of a number, and get a negative. Similarly, we can't take something times itself 4 times, 4 factors of it, and get a negative. So therefore, the part inside, whatever you're taking the square root of or the fourth root of, can't be negative. Well, sometimes it's hard to say something can't be negative and do that mathematically. So instead, if x can't be negative, if this quantity right here can't be negative, then what it can be, sometimes it's easier to look at the other end of the spectrum. What it can be is positive or zeros. So therefore 2x minus 5, whatever's inside, you set greater than or equal to 0 and you solve. And in this case, remember, if you multiply or divide by a negative, you flip the symbols. In this case, we're going to add 5 and divide by 2. We're not multiplying or dividing by a negative. So x greater than or equal to 5 halves. So that means if we're thinking on a number line, so basically that's your domain right there. So on a number line, x greater than or equal to 5 halves would be like that. Okay, so our domain is from 5 halves to infinity. And that is it, ladies and gentlemen. Radical function, simplest case. I'm going to go ahead and flip down to the fourth root. Since the fourth root, a number times itself, 4 factors of it, to get x plus 5, basically, the fourth root of x plus 5, we know that part can't be negative either, because you can't take number times itself 4 times and get negative. So similarly, on a fourth root, a sixth root, an eighth root, you're going to say x plus 5 has to be greater than or equal to 0, so x has to be greater than or equal to negative 5. And very simply, your domain is from negative 5 to infinity. And we are completely done with those two. Finally, cube roots, fifth roots. I can take a number times itself, 3 factors of it, a number times itself again, and get a negative. So therefore, cube roots, fifth roots, seventh roots, I can take negatives or positives. When I actually look at the graphs of those, they look kind of like this. They go infinitely both directions. So therefore, for cube roots, fifth roots, seventh roots, all odd roots, the domain is from negative infinity to infinity, or we talked about in the first one, that would be all real numbers. And that's the domain of radical functions, simplest form in a nutshell. The last type of algebraic domain we're going to talk about today is going to be mixing the previous types, polynomials, basic rational functions, and basic radicals. So we're looking at a combination. Basically, we're going to apply all of the situations that we have earlier. So on this first one, and I apologize for any background noise, this first one, I look and I see a radical. So we're going to have to apply that. And I also see a denominator. So to keep it simple, my first part, I'm going to say, well, 2x plus 1 can't be 0, so x can't be negative 1/2. That's a restriction that 0, we can't have 0 in the denominator. Okay, you can't divide something into 0 parts. The other part, remember square roots, this is an even root, so the part underneath is restricted to positive or 0. So the x plus 2 greater than or equal to 0, so x is greater than or equal to negative 2. So both of these have to apply. So we have basically this and this. So if I put this on a number line, it may be helpful. If I look at greater than or equal to negative 2, we're talking about all of this area. Okay? And x can't be negative 1/2. Oops, let's get negative 2 on there. And x can't be negative 1/2. Well, negative 1/2, if 0's over here, then negative 1/2 is somewhere in here. And that tells me we basically have this open circle. So, with that in mind, our domain consists of everything from negative 2 up to negative 1/2, and then from negative 1/2 to infinity. So we have these two intervals. So my domain is from negative 2 to negative 1/2, whoops, parentheses, union negative 1/2 to infinity. My third situation, or second situation, g of x, consists of three parts. We have a polynomial, which is all real numbers, no restrictions. We have a denominator, so we have x can't be 2. We have a radical, so x plus 1 is greater than or equal to 0, so x greater than or equal to negative 1. So I've got x greater than or equal to negative 1. So if I'm looking at the same kind of thing on a number line, it looks like this. But I can't be 2, so I have a hole at 2. So it looks something in this regard. So my domain is from negative 1 to 2, skip 2, and then from 2 to infinity. If you look at the graph of that, I think you're going to find that it kind of just starts at the point negative 1, has an asymptote at 2, and then goes on infinitely from there. You might want to check that out. And that is it for mixed domain.